Now let us discuss the very first question in chemistry. It is asking, if we have three Lewis acids BF3, BCl3 and BBr3, what is the order of their Lewis acidic strength? Now if you go by electronegativity, fluorine is most electronegative and bromine is least one, and therefore it is expected that boron in BF3 will accept the lone pair very easily from the Lewis base, while it will be difficult for BBr3. But the case is opposite. This is because in boron trihalides, boron is sp2 hybridized with one unhybridized p orbital lies perpendicular to the plane of the molecule, which remains vacant and can accept a lone pair from the base as well as from the halogen themselves. This results in some degree of back bonding. This back bonding is strongest in case of fluorine. This is because it involves 2p conjugation. With chlorine, the lone pair is in 3p orbital, and with bromine, it is in 4p, which is more diffuse to form a strong bond with boron p orbital. As a result, this back bonding is very strong, which results in some double bond character in boron trifluorides, which the base has to replace when it forms a sigma bond. This is because in the resultant structure, the boron becomes tetrahedral. It has got no orbital left for halogens to back bond. So this double bond character in case of boron trifluoride is lost here, which makes the reaction less exothermic, and therefore the order of Lewis acidic strength is just opposite of what the electronegativity suggests. We find BBr3 because of poorest back bonding is the strongest Lewis acid, followed by BCl3, then followed by BF3. Hence the correct answer is C. The next question is very easy. Oxygen contains 8 electrons and 2 minus, that means it has 2 extra electrons, which makes it 10 electrons. Magnesium has 12 electrons in neutral state. If we have plus 2, we are removing 2 electrons from its outermost shell. Therefore, the number of electrons remaining is again 10. So O2 minus is isoelectronic with magnesium 2 plus, and the answer is B. In the next question, we are asked to arrange the bond angles in methane, ammonia and water. In all these three cases, the central atom is sp3 hybridized. But in case of methane, there are all bonds. In ammonia, one bond is replaced by a lone pair. In oxygen, 2 bonds are replaced by lone pair. Now, VSEPR theory suggests that lone pair repulsion is stronger than lone pair bond pair repulsion, which is stronger than bond pair repulsion. Therefore, when we replace a bond by a lone pair in case of ammonia, the lone pair will command more space, which results in hydrogens to shrink closer, and therefore the bond will decrease, or the angle will decrease. In oxygen, we are replacing 2 bonds by 2 lone pairs, which will further increase the repulsion, and they will command more space. They will demand more space, and therefore hydrogen will come even further closer. As a result, what we find in methane, the bond angles are 109 degrees 28 minutes. In ammonia, the bond angle slightly shrinks and it becomes 107 degrees. In case of water, the bond angle further shrinks and it becomes 104 degrees 30 minutes. Therefore, the correct answer is B. The last case, we find potassium permanganate is a very strong oxidizing agent, and it oxidizes most of the species, even hydrogen peroxide. Hydrogen peroxide can be oxidized by potassium permanganate both in acidic as well as alkaline medium. However, the reduced product of potassium permanganate depends upon the medium of oxidation. If the medium is acidic, permanganate ion itself gets reduced into Mn2+. In alkaline medium, it is reduced into MnO2, where the oxidation state of manganese is +4, and in strongly alkaline medium, it is reduced into MnO4 2- or manganate ion, where the oxidation state of manganese is +6. So as per the question, hydrogen peroxide is oxidized by permanganate ion in alkaline medium, and therefore MnO2 is formed from permanganate ion, and the oxidation state of manganese in the reduced product is +4. Therefore the answer will be D.